Okay, so welcome back to one of our last lectures. And it's we're going to cover a topic today that I find fascinating, more so than any of the other machine learning concepts that we've covered. And it's called reinforcement learning. It is distinct from supervised learning and unsupervised learning, but it's just as old. It's been around since the 1950s, and it's, well, the reason why I think it's so interesting is it's the closest of all of the machine learning techniques to actual human learning. And in recent years, it has seen a lot of very interesting to me applications. So I'm excited about it. Now, it is its own field. It's a huge field. In fact, this is a thick book on reinforcement learning. It's like the go-to book. And this is typically covered in 2 semesters. Right, so we do not have time today to really dive into it. This is sort of why I want to create a second course this summer on reinforcement learning and deep learning and putting these things together. Okay, so, all right, let's go ahead and dive in. So what is reinforcement learning? So this is a computational approach to automating goal-directed learning. And decision making. And I should add on to this probably sequential decision making. So, okay, what do I mean by this task, right? In supervised machine learning, we have data, and we have the labels for the data, and we use that information to somehow make predictions on unseen data that are similar. Okay? In unsupervised learning, we can cluster the data in several different ways. In reinforcement learning, the problem is almost completely different to me. It turns out that it is fundamentally related, but it just feels different. And by that I mean, okay, suppose do you all know tic-tac-toe, this game? Tic-tac-toe, so it's called X's and knots in other countries. It's basically you have a board like that, and then player 1 puts down an X, and then player 2 puts down an O, and then the goal is to get 3 X's either on a diagonal, a row or a column, or 3 O's, right? So a full gameplay would be like this. And then, X is 1, right? But notice that at each step of the game, I had to make a choice, right? So I looked at the original grid and I observed it, right? And I said, I'm gonna put an X right there. So before I did that, this was the state of the grid. And I had to choose an action, right? So the action that I chose would be that action. And when I chose that action, the environment responded and put a node there. And then I had to make another decision. Where am I going to put my next X, right? And then once I do that, the environment updated and they put a node, right? So how do I know to do that? How do I know to make these decisions? Well, there's I kind of have a strategy in my head, right? I knew for sure, okay, as soon as they put an O there, I knew for sure that if I put an X right there, that I win the game, right? So the value of that action in this state, to me, was highest. That would be much higher than if I put an X there, right? But maybe the value of an X there would be something as well, because it blocks them. So among all the possible actions I could have taken, this was like the highest value. This was the next highest value, and these probably didn't matter at all, right? But like, suppose like I make this action here, right? Then there's like O's can do something else like that, right? So then maybe I would put an X there and win, right? And then each action I take, there's like some type of value that I'm observing, right? At each iteration of the game, there's like a value that I could interpret, right? And the environment is kind of speaking back to me. Like I act on the environment and then it does something. And then I look at it and like, oh, like, so like, if I would have done this, right? Like, well, actually any X I pick is good at this point, right? So that maybe that was like a good action as well. Maybe that was just as valid if I would have put it there, right? So it just depends on how you like measure your reward in playing the game. Of course, you want to win it, right? But each action could give different types of rewards. And the way that we're going to model this idea and learn the appropriate rewards is through like experience, basically. We're going to play the game really dumb and observe what happens a bunch of times. And then we'll start to learn the values of the different states, right? Like this state here is like very valuable to us. Much more so than like that state, right? So each state that I observe is going to have a different value. And then each state action pair is also going to have a different value. But back to our general model. Okay, so reinforcement learning consists of two things. Something called an agent, which that's like kind of like how I was acting, right? And then an environment. In this case, the environment would have been the tic-tac-toe environment. But you can think of the environment in a bunch of different scenarios, like maybe landing like a lunar rover on something, right? Or a car driving. Right? There's different actions the car can take, and it's observing each couple seconds the road, right? So there's many different applications of this type of model. So the environment initially will provide the agent with a state at time t. Okay. And the agent observes that state and then chooses an action. At time t. Just like I was playing the game over there, right? And then the agent informs the environment of their action, and immediately the environment sends the agent a reward at time t plus 1. Okay. Right. So, and then also it will update the state to be the next state, as t plus 1. And then the agent observes state t plus 1, makes another action, receives a reward. And this is like a control loop here, just goes and goes. And for our purposes, we're going to consider that this control loop will have a terminal state. It will eventually stop. There's like a maximum number of steps it will take, or like the game will finish for our purposes. Some of these problems you can just model as going forever. But for our purposes today, just every control loop that we observe will have like a finite number of state action reward triples. Okay. So what is this diagram? Well, this diagram is a model of what's called a Markup decision process. Okay, so I'll just always abbreviate these with MDP. And this is just like a classic formulation of a sequential decision-making process. That's all that this is, okay? Let's see, what was I going to say next? So this is like a field on its own, outside of reinforcement learning, like understanding MDP's own field. It just happens to be the case that, so this is like Markup decision process, and then that reinforcement learning, or actually I should reword this. Markov decision processes are, let's say, mathematically idealized formulations of reinforcement learning problems. Problems and models. So they're like a clean version of reinforcement learning problems. Okay, but in both MDPs and reinforcement learning, we have agents and environments. So just for like definition purposes, the learner and decision maker that's the agent. Okay. The thing that it interacts with is the environment. So it's important to never forget that reinforcement learning consists of these two things at the very, very highest level, an agent and an environment. Sometimes when you're working with reinforcement learning algorithms, at least in my own experience, I kind of forget about the environment because I'm focusing so much on what the agent is doing. Right? I'm trying to get the agent to learn something, right? But I forgot a detail about the environment that maybe I should have customized to be a little bit different. For example, the reward structure. Like choosing how the environment responds with the reward can be a very important thing to consider when doing all of this on your own in like a research type of problem. Okay, so agent environment, this loop here, this is an MDP, and reinforcement learning problems are like messy MDPs. Okay. Okay, so we have this like loop, and this loop is going to generate a bunch of these values, right? It's going to generate a sequence. Okay, so the terminology for this, so the agent and environment interact at each discrete time step t, 0, 1, 2, 3, so forth and so on. And generate what's called a trajectory. And that trajectory is precisely this: state 0, action 0, reward 1, state 1, action 1, reward 2, dot, dot, dot. Okay. Now here, just for more terminology, S sub t is an element of script S, the state space. A sub t is an element of the action space. R of t is the reward space, or is an element of the reward space. And that's just some subset of R. And for our purposes today, we're going to assume that the action space is the same for every single state. And that's not always going to be the case. But for our purposes, in a simplistic case, this space A, script A, stays the same throughout all of the process of generating a trajectory. Okay. And for our purposes today, we can assume that this is a finite set here, the state space. We can observe a finite number of possible states that can occur. So like tic-tac-toe, for example, right? There's a finite number of states, okay, that you can observe, right? There might be a lot of them, right? But finite. Now, for something as small as tic-tac-toe, we could possibly write like a decision tree type of structure, possibly, right? We could literally like enumerate every possible position in choice of action and just follow our way down to win, right? We could possibly do that. But something like chess, we could not. Right? There's no way that we could enumerate every possible board position combination of pieces. I don't even think that number is actually known in this case. Like, yes, you can know every possible like covering thing. It's like a simple counting problem, but I don't think it's known every possible position, taking pieces off, looking at different combinations of pieces, things like that, in like next states doing that over and over. I don't even think that's known. It's definitely more atoms than there are in the universe. I'm pretty sure that is that. So we definitely can't enumerate that. So because of that, we have to be like clever about how we think about getting the agent to do better and better and better. We can't just like give it a table to follow or a tree to follow, a decision type of tree. So we're going to assume finite, finite. Okay, so when these sets are finite, the random variables, so, okay, so I'm running out of room. So in finite MDPs, we should say cardinality of script S less than infinity, cardinality of script A less than infinity, and cardinality of script R less than infinity. Like I was just saying, so that's what we're dealing with. We're dealing with finite Markov decision processes. Okay, and in this case, we know something about RT and ST. So in this case, we know the random variables R of t and S of t. So the reward at time t, the state at time t have well-defined discrete probability distributions. Okay, so what does this mean? It means that there's a function, a probability function, that we can associate with a state S and a reward R. So, if, let's say, S prime is an element of the state space, and R is an element of the reward space, we're going to say that little p of S prime comma R bar SA is equal to the problem. This is like a definition, by the way. This isn't like any derivation. This is a definition. Probability of state T equaling S prime, RT equals to R, such that ST minus 1 is equal to S, and AT minus 1 is equal to A. This is just a definition. In fact, sometimes people, I don't know why, but sometimes people do that just to mean definition. It's just a conditional probability. So this is the probability of finding yourself in state S prime and getting reward R, given that you're currently in state S and you take action A. So in finite Markup decision processes, this function determines like the behavior of your system. If you think about that, right? Like this is telling you the likelihood of you finding yourself here in that state with that reward, right? Given that you're in that state and you take that action. So this is determining the dynamics of this control loop. It's like an optimal control loop. So in a sense, if you know this probability, which sometimes in engineering systems, you know that probability, you can kind of plan, right? Like, you know, like for example, suppose like S prime is like I don't know, so just suppose that this is like a really high value, right? You can anticipate to be in that, like get that reward and be in that state. You can anticipate, you like have some type of like look ahead information if you know the probabilities of landing there, right? Like think about like maybe like S double prime R double prime or R prime, I don't know. It's like that's one like state reward pair that you end up in for that, right? And then another one is S prime R. So there's like two options that you can land at. And you're there and there, and these are the two options you can land at. And you know the probability of landing there is like twice as high as that, right? Then you can plan for being in that scenario next, if you know that probability function. And so that the distribution on these variables when you have finite sets can be useful to know. However, we're going to pretend that we don't know this. We're going to pretend that we don't know the environment transition probabilities. And we're still going to somehow be able to learn. Now, in a lot of engineering tasks, like optimal control and what is it? What is that other thing? Let's see. Yeah, like so finite Markov decision process in the most ideal form, a lot of times you know that probability. In dynamic programming, which I'll talk about what that is in a moment, you also know that probability. In reinforcement learning, a lot of times you don't. And that's what we're going to try to like learn about today. Okay. All right, so there is a very important assumption that we need to make though, before we go any further, because without this assumption, things become very messy very quickly. And it actually becomes like almost impossible to learn anything if we don't have this assumption. And that assumption is that our mdps, the ones that we're looking at, follow something called the Markup property. So we're assuming this very important property. We're assuming this. Okay, so we're assuming that the probability of each possible value for S sub t and R sub t depends right, only on the immediately preceding state in action. Okay, so that's what we're assuming throughout all of these control loops. Meaning that when I'm observing the state that I'm at, I'm trying to figure out what's going on in the next state, what the reward is going to be, the next state is, I'm not assuming anything prior. I'm just looking one step ahead. And the state I'm in is the only thing that's going to influence that next state at that discrete time step. Okay. Very important. Now, so how do we get the agent to make better actions, right? How, like, what? Still, like, I've just been writing a bunch of terminology right now. It should seem very daunting to get an agent to learn to play tic-tac-toe or to drive a car, right? But we'll get there. But as with a lot of machine learning, especially supervised machine learning, we need to optimize something. We need to find like the highest value or lowest value or something. So we need to associate with trajectories and subsequences of trajectories called episodes, values that we can like maximize. Right? If the agent is getting a reward at each state action selection, right? Then maybe we want to maximize rewards over a given episode. And an episode is a subsequence of a trajectory. So maybe I should just write this down for your notes. Like, yeah, okay, so at each time step, just recall that the reward is a single number. Right, and the reward is provided to the agent by the environment. Okay. So the agent's goal is to maximize the total amount of reward it receives. During play, right? Before termination. Let's say that. I like to think of these as games, so I'm going to use that terminology a lot, so during play. Okay, so I'm going to denote the terminal state, the state where we finish by capital T. Okay, so in particular, for like, okay, so for an episode, and again, an episode is like a subsequence of a trajectory, but we can just partition it into little pieces. So for an episode, state 0, action 0, reward 1, state 1, action 1, reward 2, all the way up to the terminal state T. So it's a finite sequence of state, action, reward triples. We have a discounted reward. For that episode. Not for that episode, we have a discounted reward for each T equals 0, 1, through capital T. We'll talk about that in a moment. Let me write it up there first, and then we'll discuss what it means to be discounted.
Inflation.
So, okay, and it's given by this. So at time step t, so the discounted reward is called g of t. That's equal to the reward that you get the next time step plus gamma times the reward you get at the following time step plus gamma squared times the following time step plus dot, 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 all the way to the terminal state, where zero less than or equal to gamma, which is less than or equal to 1. So gamma is called the discount factor. Okay, so the choice of gamma really depends on the problem at hand, right? So for example, like this G, right? This G of t, it's like you're in state t, right? And you take some action and you move out of that. There's all different types of actions that you can take from that state. And you're going to play the game until termination. So you get an immediate reward. That's the word that occurs after that time step is up, like transitioning to the next time step. You'll have some immediate reward. Now, think about it maybe in terms of like money. Like sometimes you would take $1,000 today versus waiting a week and then maybe getting $2,000. You're not guaranteed 2,000, but you're guaranteed 1,000 today. So depending on what your goals are, if you were more concerned with the money today, then you set gamma equal to 0, and you would just look at your immediate reward, right? Not even caring about what might happen further down the line. But if you kind of want to think about that possibility of getting that 2,000, set this equal to like 0.5, maybe, right? So there's this reward plus like somewhere down the line you might like want to incur that and like get some benefit from that 2,000 maybe. If you wanted to care about every single reward at every single step following this time that you're in, set it equal to 1, and then it's just all the rewards to termination. Okay, so we should do a little bit of algebraic manipulation on this thing real fast. Because right now it's just like, how would you even calculate this, right? Like you're playing an episode, right? Like it doesn't seem very easy to calculate right now. So what we can do is rewrite it. So, and I'm going to leave this up for the rest of the lecture because it's going to pop up again. So, we discounted reward at time t. G of t. I'm just going to rewrite it real fast. But then I can factor out a gamma from all of those terms there. Okay. We know we can factor that, it's finite. We know that the episode terminates at some finite step. That's what we're assuming. But then look inside of there. Rewarded time t plus 2 plus annual times time t plus 3 plus dot dot dot. That's the discounted rewarded time t plus 1. So what this is implying is that we have like some type of recursive way of computing the discounted reward starting at time t. Okay. All right. Now, we have a way of measuring the reward to follow being in state t and taking action t. We have a way of like somehow measuring the cumulative rewards that follow it, discounted cumulative. So now we need a way of like measuring value of a state or value of a state action pair. Okay, so this is like a subsection. So policies and value functions. Okay, now, so a good quote here. So almost all of reinforcement learning algorithms involve estimating these things called value functions. And value functions are functions of states or state action pairs that estimate how good it is to be in a given state. Or good to say take action in state. So for the state action pair. Okay, so now we're talking about functions, right? So we're going to consider two types of functions that measure how good it is to be in a state and how good it is to be in a state and take an action. If you think back to tic-tac-toe, there was obviously that really good state, right? So how would we measure that and compare it to the other states that could have been in, right? And if I knew a function that told me that the value of that state was higher, remember that really good state, right? If I knew a function that told me the value of that state was higher than the other ones, other states, then I could maybe take actions to get to that state. Okay. Which leads me to the next definition. I kind of already said it. So a policy is a mapping from states to probabilities of selecting each possible action. So policies are how our agents select their actions. That's all it is. But they're non-deterministic in learning. And I'll get to why that is in a bit. But basically, if you have a mapping from the states to a probability distribution, you can just sample from that distribution. That's the action you take. So, like action A, action, they all have like weights in this like box. And you just blindly sample out of it. The one with the highest weight is the one you'll take. And the weights come from this, the value functions. So it's almost like each action, each state, or each state action pair has like a volume in this box. Like imagine like a box. And the volume for each one of those state action pairs or states is determined by these functions. So if you know these functions, you know the volume of how much they live in there, and you just sample out, and that's your action. And why would that be good? It's because these functions are measuring how good it is to be in that state action, to take that action in that state, or to be in that state. So these functions should measure somehow the discounted reward following being in that state. Right? If they measure this accurately, then you just have a distribution that you can form from them, and then yeah. Okay. So there are two functions that we'll consider that measure this. We're only going to use one of them, but I'm going to mention both of them. So, okay, I'm going to stick this right there because I need all of these to be next to each other because they're going to stay for the rest of the class. Okay, so the first one, okay, I need to write a little bit above it. Okay, so following policy pi, for all time steps, greater than or equal to t, we have two value functions to consider. V subscript pi of s is the expected value following policy pi of the discounted reward. And this is given that the state at time t is little s. So like value, this is called a value function following policy pi of state s. And it's an expectation, which is an average value, right? The reason for this is that in general, okay, there's like two reasons. Policies are not deterministic. So just because you're following this policy pi in that state doesn't mean you're going to take the same actions playing the game over again. You might vary a little bit, right? Also, sometimes in environments, the environment responds with a different state following it. Does that make sense? Like playing tic-tac-toe, the player can put the 0 anywhere it wants, right? So one episode that you play, you'll get a value for this following that policy, starting at that state there. Then for another episode, you might get a different value. For another episode, you might get a different. This is looking at the average over all of them, which means that you would have to play the game a bunch of times if we have any hope of ever wanting to learn this. Which, by the way, the reason why we'd want to learn the value function for a given policy pi is that once we know the value of that state S following this policy, then if we find a policy that gives a higher value function, then we know we're doing better because we're getting larger discounted rewards following that other policy. So, but we're not going to use this one today to program anything. We're going to use the next one, which I like a little bit more. This is called the Q function. So this is the value function, this is the quality function. This is the expected value following policy pi of the discounted reward such that you're in state S of t at S, and at time t, and you take action at time t. So this is a state action reward function. And so this is measuring the quality of being in state S at time t and following policy pi. This is measuring in state S taking action A. Now that's actually very useful for us because now, like, in order to use the value function, right? This is just telling us what the state, like the values of the states are. Like, so we'd have to like sample, like, okay, if I take this action, what's the state going to be? This action, we'd have to know the dynamics of the environment a little bit. With this though, right? If we know the quality of taking action A in state S, right? And there's only like 3 actions. And this is measuring the expected discounted return. Wouldn't we just want to take the maximum action, the argmax? Like one of the actions you pick is going to have the largest expected value, like on the discounted return. So take that action, and you find yourself in a new state, take that action. So if you know this function, you can form a policy, right? You can update your policy to always take like the best Q value. Okay. Now, in general though, like, okay, so policies are just, again, they're just mappings from states to probability distributions on the action space. That's all it is. So there's going to be a bunch of different policies that take for a given environment. The simplest one would just be every action has equal probability. So it's just randomly picking an action, right? That policy will assign like a value here and a value here. Like you can calculate that, right? But surely there might be a better policy that you could follow. You'd have some other policy that would do a little bit better than the random policy, right? So we can just like acknowledge that, like, okay, maybe for each state action pair, there's probably like a better policy to follow. It will give you a higher Q value, right? Because this value here is determined by the policy, right? You're taking that policy, and then you're observing the reward and the discounted reward thereafter, right? So what this does is it gives a partial ordering to your policies. And we're going to imagine, theoretically, that there is some best policy for every state action pair. There is a best choice that what maximizes your discounted return, your expected discounted return following that policy after time t. So if we knew that policy, then we could maximize the action choices that we take, just like I said earlier, right? Like, if this is like the optimal policy, and we know the expected value taking action A in state S, and then we also know the other action, and you have like there's 3 of them, and this is the optimal policy, we just take the action that has the largest value right there. And then we take the largest value again in the next state, and the next state, and the next state. So if we knew that function that under that policy, then we're good. We know our policy. Right? Does that make sense? But it's almost like we would need to it's like we're like answering the question that we're asking in a sense. Like if we knew this, then we're good. But how do we know that, right? How do we find that policy? Yes.
So policy, is it this set of all steps, or is it just the current?
It's a single policy. It just maps whatever state you're in to a probability distribution.
So it's a single step.
Yes.
So this is my code.
Yeah, it only matters that like all the previous ones don't matter. It's just like one to the next. And because we're assuming that the actions don't change over the states, it's just the same function of the whole time.
So the problem is now, like, we don't know what are the weights, right?
We don't. So there are no weights right now. There are just like values. Like we don't know the values of this, but how we can find them though. That's the next part of the lecture. Like we actually this one. This is the one we want. We don't want that one. That's bad. We want the best Q function. So for this given policy, this best policy, there is a Q value associated with each state action pair. Okay, that's very important. For that policy, there is a Q value for each state action pair. And those numbers tell you the expected return, the best approximation to the expected discounted return following that policy. And if we're trying to maximize these things, we want to maximize that, then we want the maximum expected return. Okay, and if we know that, right, if we know those Q values, then we can choose, right. In fact, I should probably write that down. This is very important. So I'll call this Q star is like the optimal instead of pi star. So this is like the expected value of r plus 2 plus 1 of gamma times max A prime Q star of the next state you find yourself in, A prime, such that ST S A of t is equal to A. So maybe I should say this. So this is the important part. Once one has this is what I wanted to say. The value of a state or a state action pair under an optimal policy must be equal to the expected return for the best action in that state. That's what I should have said earlier. That's the important part I left out. Okay. So optimal policy. So the value of a state or state action pair, value of a state in particular, under an optimal policy must be equal to the expected return for the best action in that state. It's like a finite number of actions you can take. One of them, the best one, is going to lead to the best expected return. So if we know the values of, like, for each SA, we know the values of this, then we just take the best action. All right, I'm going to go ahead and pause the recording here so we can take a break. Okay, so welcome back. All right, so what we just kind of went over was that there are trajectories in episodes generated by this optimal control loop of an agent in the environment. We discussed the discounted reward, which is this recursive formula here, which measures the amount of reward the agent should expect, well, not expect, but the amount of reward the agent will receive starting time t. Okay, and then we discussed, okay, for a given policy, which a policy is just a mapping from states to a probability distribution over the action space, following that policy, whichever it is, we have a way to measure the value of being in state S or the value of being in state S and taking action A, which are the expected values over a bunch of different runs of episodes following that policy. Now, if we're able to determine the optimal policy, the optimal policy is always going to give us the maximum Q values for a given S and A, right? If we know that optimal function, then we can alter our policy to always pick the largest Q values for a given state action pair. Okay, so the way that we're going to do this is with two algorithms. Both of these algorithms fall under the realm of what's called temporal difference learning. Now, I'm skipping two major aspects that I should, like any reinforcement learning course I would normally cover, but I don't have the time to today. So temporal difference learning is a mixture of two different types of things, of two different types of ideas. So this is a combination of ideas from dynamic programming and Monte Carlo methods. So to summarize, and like this is just such a quick summary of what this means. So dynamic programming solves these Monte Carlo type of simulations recursively. And Monte Carlo methods are a generalization of the two methods I'm going to discuss today. Oh no, the two methods I'm going to discuss today are generalizations of Monte Carlo methods. Basically, Monte Carlo methods will, like, suppose we want to like estimate the optimal value function, right? There is some like optimal value function as well. There's not just an optimal Q function. So like Monte Carlo could do something like, suppose you find yourself in state ST, you can update your state like this. Oh, I think I miswrote that last one. No, I didn't. I don't know why I don't question myself. So like Monte Carlo would do something like this to update V. So V here is like, we want V to approximate V star, right? So like the optimal value function, right? So what we could do is we could initialize V at every state to be a certain value and then update with this rule. Hopefully this rule looks familiar. In gradient descent, what do? What is gradient descent? Like, just to recall, like, this is not what we're doing right now, but like, what is it like? Weights become weights minus alpha times the grad of the cost at weight, right? And what is this often? This is like, this often we've seen it. It looks like this, y minus y hat, right? That's like your error term, gradient descent. Gradient descent is used for minimizing problems, right? What are we trying to do? We're trying to maximize. So if we're going to maximize, we use something called gradient ascent, go uphill. That's our old value. Let's go uphill, learning rate times, that's the true value, right? If we're trying to approximate the value, the optimal value function, right? And G of t is like what's going to happen, what actually happens when you take that, when you're in that state. So this is like your y, and this is like your y hat. This is your approximate to that. You're trying to get to that. You're trying to like maximize it. Okay. So Monte Carlo methods would look something like this. But notice G of t though. G of t, like truly, you have to calculate, you have to take your action, find that, but then you have to do the same thing there, same thing there, same thing all the way till termination. So Monte Carlo methods will update your approximate value function after running through an entire episode, which can be highly inefficient. Temporal difference methods update at each time step. And there's two of them. So one is called an on-policy method, and one is an on-policy method, and it's called SARSA. And instead of the value function, we're going to approximate the Q function, because I want to know the actions to take, right? If I'm in state S, and I have several actions to choose from, and I know the optimal Q, then I just pick the one with the highest value. And that's the action I'll take. So for all of these methods, okay, I'm going to get rid of this Monte Carlo thing because I guess it's relevant, but we're just talking about temporal difference right now. And we're not talking about the value function. So let's Q for each state and action. We want this, or maybe we want to build a Q that's an approximate to Q star for each state action pair. We want to build that. And if we can know that if this is a good approximation to this function, and we know this value for each state action pair, if we find ourselves in that state, we take the action that maximizes that value, because that's what this is doing. It's trying to find the optimal, right? So for SARSA, we update as follows. So our old estimate plus a learning rate, alpha, a number between 0 and 1, times this. I'm going to change the notation a little bit. Okay, two things to note here. It looked like that thing I just erased, right? Okay. So here we need 4 things though, or 5 things. So we need, we're in state S, we take action A under our policy, and then we get back a reward and find ourselves in state S prime and then take action A prime. So in order to update our Q approximation for SA, we need to have all of these things. That's why it's called SARSA. And it's called on policy because the policy that we have, whatever it is, which I haven't told you what the policy is going to be, the policy pi determines A prime. That's why it's called on policy. And once I tell you what the policy is going to be, you'll understand this a little bit more. But let me write down the rules first. Okay, so the next algorithm is going to be an off policy algorithm. And it's one of the most famous algorithms, I think, in reinforcement learning, and it's called Q-learning. It's going to look very similar. So here, notice that the only difference is this max argument here. The choice that we picked, like the value of in here that we pick, is dependent on the maximum of these values, not the policy. The policy here is going to give us the next A prime, right? In this sequence, we're in that state, take that action, we get a reward, find ourselves in that state, and then our policy determines that. Right. In this instance here, we have the same state action R as prime, but we don't need, like, regardless of what our policy says is going to be the next action, it doesn't matter. It's always going to be the max of those values. So this is why it's called off policy. So, okay. What are these, like, okay, so this is like some type of function, right? Question.
Is there a discussion vector for Q?
Oh, yes, yes. Thank you. So like now, these like terms are like our error terms. Right, like this is like somehow like this thing here, or somehow approximating that. Right, look at it. R plus gamma times the rest, right? And if our Q is approximating that well, then it's good, right? There's just two different ways of doing it. So this is like our actual label, all of this here, and that's our proposed label. So think about supervised learning. It's just now we have to play the game to get the labels at each step. So we take an action, we get a label, we compare it to what we thought it should have been. Like think about it, like if this whole term was equal to that, then we had like basically got the perfect prediction already. This is 0, that doesn't change. If this is bigger than that, then we're underestimating its value and we need to like add a little bit to it. If this is smaller than that, then we're overestimating and this will be negative and we'll subtract off a little bit from that. And through playing over and over and over again, we can start to update the values here. And what's nice for the types of problems we're considering today is that there's a finite number of states, a small finite number of states, and a finite number of actions. So what we can make is something called a Q table. And what does this look like? State 1, state 2, state 3, dot, 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 state M. Need to get rid of that, make it over here. Table. Action 1. Action 2, dot, dot, dot. Action N.
So the big QSA is our prediction, right?
It's the big Q is the value for this state action pair that we wish to be close to the maximum value under the optimal policy.
Ah.
Like if we can somehow get close to like each of those pairs being basically that, then we can form a policy, a new policy, by just taking the argmax action. So what we can do is we can start with a table of zeros, basically. We can start with a table of zeros, initialize our environment, and have our agent follow some policy, and then start to like update this grid with these values. But the way that we're going to do that is special during learning, not while using the thing. So for learning, we're going to use a very special policy. We will use an epsilon greedy policy. Okay, so what this is going to say is something like this. So the probability of selecting action A, or no, I'll have to write it out with words. So, in state S, choose choose the argmax A of QSA with probability one minus epsilon and randomly with probability epsilon. That is the epsilon greedy policy. So why would this make sense? Okay, so suppose like we're in state 2 to begin with, right? And we take the argmax of that row. So we end up like taking like that one, like right when we start, and everything else is 0, right? So then maybe we add something in here, like 0.5. Then, okay, the next time we come here, we're always going to pick that if we chose the argmax. We're never going to explore to see if other actions in that state are better. So that's why we need to sometimes, with probability epsilon, sometimes don't pick that. Pick something and explore, because maybe that action is better than taking that action in that state. It's exploration versus exploitation. Yeah, so the higher values towards like after you've played a bunch of episodes, the higher values will probably be better, right? But when you're learning that table, when you're at the beginning of learning, you need to explore in order to see all the possible state action pairs, right? Like, and this is a problem sometimes because sometimes the agent will never experience like that state, right? Or we'll only experience it one time. You need to play enough to where with this policy that you kind of randomly end up there and you get to fill in those values with non-zero entries. Okay. So hopefully you have these in your notes, that update rule and that update rule. Now I'm going to show you how they work programming wise. So I'm going to pause the video and then get set up. Okay, so here is a Jupyter notebook I've loaded up that I'll provide all of you probably later this weekend. I just have to put some work in to change some things. And in this notebook, we're going to implement both SARSA and Q-learning. Now, to do this, we're going to need to install a few things. Now, there is a Python package called OpenAI that's funded by Elon Musk and other people to make reinforcement learning tasks more accessible for people to experiment with. And that's what we'll be using today. Now, on my Mac, I needed to first pip install these dependencies. These do not come with Anaconda, so like Gem doesn't, I'm pretty sure Pygame doesn't. Pygame will be used for visualizations, but you might have to run that stuff. Okay, so let me just go ahead and import some things. So matplotlib, numpy, seaborn. I'll be using random for sampling, IPython display for displaying rendering environments, Gem for the Gem environment, and sleep to kind of pause the environments while you're watching the frames go. And then here, I wrote a custom function that'll make it easy for you to visualize the frames of the environment or the episodes being played by the agent. Okay. Okay, so maybe I should click on this link real fast and then hold on 1 second, it's loading. Okay, so here is the documentation for OpenAI in Gem. And as you can see, there's these little environments here that they provide you with that you can run machine learning algorithms on. They provide interfaces for tabular reinforcement learning like we're doing, and then also deep reinforcement learning when you cannot enumerate the possible states and you need to pass the states into a neural network as an input vector and then predict out probabilities instead of using a table. Okay, so I encourage you to go look at this documentation. It's okay. It's not bad, but it's dense. So just keep that in mind. Okay, so the Gem environment env, but that's how you typically will load them in, is a Python class with a bunch of methods and attributes. So again, I encourage you to go to the documentation. However, I'm providing you with like the basic info here. So there's reset, which resets the environment, take a step in this action, observe, reward, done, and then info. And then render if you want to look at the environment. And the environment that we'll be looking at today is the Taxi V3 environment. So this environment is a grid consisting of locations to pick up a passenger and to drop off a passenger. There's also walls that you can't drive through. And the goal is to teach the taxi to drive around this environment and pick up the passenger at a location and drop them off at their desired location. So there are 500 discrete states, and that's because there's 25 taxi positions, 5 possible locations of the passenger, and 4 destination locations. So if you multiply all this together, you get 500 possible states, right? So just think about like, there is the static state of like the walls and stuff, but then there's like different places where you can get picked up and dropped off, and the taxi can be in a bunch of different states. Right? All right, so the passenger locations occur at 0, 1, 2, 3, or 4. Destination 0, 1, 2, or 3, and they'll be shown in colors when we look at it. And the action space. Okay, so finite action space. The taxi has 6 possible actions: move south, move north, move east, move west, pick up, and drop off. So think about the table that we had. Like there's going to be 500 states, and there's going to be 6 columns. So 500 rows, 6 columns. And each entry in there is going to be a Q value that we're going to try to learn. And the argmax should be the action that we take. Okay. All right, so here is, I'm going to make my environment. I'm going to reset it, print the initial state, and then run it. Okay. And notice when I reset, the taxi just randomly appears in there. So here, the taxi would need to navigate to the blue G and then navigate back to Y. Okay, so I should probably mention the reward structure here. Every time step, the taxi cab receives a reward of -1. except for when it delivers the passenger, which is a plus 20. It also receives illegal, like negative 10 if it picks up in the wrong spot and drops off in the wrong spot. So it's like really incentivizing what? Not to drop off in the wrong spot, not to pick up in the wrong spot. But then also it's incentivizing dropping off quickly. Right? Those -1s are incurring every time step, right? So we want to maximize these rewards. And just to demonstrate how the gym class works, the environment class works, I pick a random policy. So env.action space is a set of actions, and I'm going to sample from it, just randomly sample an action. And then I set the total number of time steps at most 50 per episode. And then done is one of the things that's returned by taking a step in that direction. So action is equal to a random sample. I pass it into the step method of the environment. So that's my agent telling the environment I want to do this step. And then the environment returns the next state, the next reward, is it terminated, and then an info dictionary thing. And then I'm tacking onto the reward and I increment my I just for counting purposes. And then I plot the rewards. You can see that it's everywhere. It's random, right? It's randomly picking up, dropping off, taking left, right, up, down. It doesn't know what to do. Funny though, when I taught this at UHD the other day, on the first run, it did it randomly. Randomly picked it up and dropped it off on the very first run. I've never seen that happen before, but I guess it's possible. Okay, so we have our table, as I was mentioning in lecture, and we're going to fill this using both Sarza and Q-learning and compare them. So the way that I did this, I might change it, is I created my own custom class called agent. It takes in a gym environment, immediately instantiates a matrix of zeros for the Q table, and then it makes a rewards list to keep the rewards during training. Okay, so first up, we have Q-learning. We have the discount factor set to 0.7, learning rate 0.2, epsilon. So that's the probability of picking a random action for the epsilon greedy policy. And then I'm going to let it play 1,000 episodes to populate the Q table. All right, so assume that the initial state is not terminal. Total reward is going to count the rewards incurred over that episode of play. Reset your environment. You always reset your environment after you finish. And then here is my first epsilon greedy choice of an action. So random.uniform from 0 to 1. If that's less than 0.1, take a random sample from the action space. Otherwise, take the argmax from the Q table. Okay, so while not done, so it's going to play the whole episode. There's no limit on the time steps right now, so it's going to keep on going. Next state reward done info is equal to step in the current action, which is up here, right? It was either random or the max. Another epsilon greedy choice to get the next action, right? Yep. Then I find the max of my Q table, right? That's the Q learning algorithm. We take the maximum value from the Q table in that given state. So the max along that row, right? The policy doesn't determine what that choice is. My old value is just the Q table at the current state, current action. That Q of S comma A, that's what that is. This is max of S of Q S prime over all A. And then I update my Q table. There it is. Old value plus learning rate times that. It's exactly what I had on the board. Increment my reward, move my current state to what was my next state, because I'm going up in time. Current action, next action, continue. Append to my rewards. Sarza, same thing, except for right, where is it? Here. I know, Sarza value. It's not the max of the Q table in the next state, it's the one predicted by the policy. So that's why it's on policy. All right, so I run that, make a Q agent, Sarza agent, and then I train them over 5,000 episodes. I don't know why I incremented my gamma. I'm going to leave it at what it was. I think it was 0.7. So that's the Q agent. Look at the rewards. There's the SARS agent. So now I'm going to plot the SARS agent rewards in light sea green and the Q agent rewards in light sea green. Differences in behavior for sure. But a lot of this has to do with like the parameters used, like the gamma and the alpha. Okay. But you can see that the rewards for both are now much higher than where they started. And again, we're maximizing the rewards over each episode. So these are the episode numbers. So on the x-axis is the episode number, and on the y-axis is the cumulative rewards over that episode. So then here, I'm going to look at my Q agent actually playing now. So now, so like frames is equal to empty list, and do this 10 times, reset my environment. So the environment's tacked on with the agent when I make that class. And then inside of my agent class, there's a greedy policy. It's just taking the argmax without the epsilon. It's just greedy. So it's taking the argmax of the Q table as its action at each state. And then I pass that action into the environment. I put inside of this frames list a dictionary. And then at the very end, I print frames, which is that custom function I wrote up top. And it looks like it's picking up and dropping off pretty good. Except for there, it got stuck for some reason there. But yeah, you can see it learned something. It's not random, for sure. That's kind of cool, right? That didn't take much work at all for it to learn to pick up and drop off. SARS, it looked like it was doing a little bit worse in this case, so maybe I'll look at the SARS agent now. SARS. So let's look at that now. Yeah, it's kind of not as great, right? Yeah, it's probably I don't know. It probably didn't train enough, and probably the gamma was too high. Let's try again. Again, this is stochastic in that when it's reset, it's different states to begin with at every time, so it's gonna behave different. Now it's stuck there. But again, if I go back to like Q in this instance, the off policy method. Okay, so now I want to show y'all a really cool video. But first, this is just the very tip of reinforcement learning. The really interesting things are the cases where you cannot enumerate the state action space. In that instance, it's been shown now, and this is where the cool stuff is, that you can treat the state. So what were we doing, by the way? We were like trying to approximate a function, right? The Q function, the optimal Q function. What do we know that's really good at approximating functions from supervised learning? Neural networks are the best function approximators that we can think of. So in deep reinforcement learning, the states are fed in to a neural network, and the neural network outputs probabilities of action 0, 1, 2, or 3, or 4. And then like similar states will have similar outputs, which is good because you can't see every single possible state, right? So if you encounter a new state, it's not like it's an empty value in the table. It's similar to one of the ones you've seen before. And the neural network, if it's trained properly, should output the correct probabilities. Now, on that note, I have a video for you guys to watch. It's like one of my favorite videos to show people. I show people at bars this all the time. Reinforcement, because they always ask me what I'm doing, and I'm like, watch this. This is what I want to do. By the way, if you don't follow 2-Minute Papers on YouTube, you should. He's like one of my favorite YouTube channels.
After saving with customized car insurance from Liberty Mutual, I customize everything, like Marco's backpack.
Is rolling back prices
Okay,
on our best-selling mattresses. Right now, get 0% interest for 60 months on select.
Minute Papers with Károly Zsolnai Fehér. In this project, OpenAI built a hide-and-seek game for their AI agents to play. While we look at the exact rules here, I will note that the goal of the project was to pit 2 AI teams against each other and hopefully see some interesting emergent behaviors. And boy, did they do some crazy stuff. The coolest part is that the 2 teams compete against each other, and whenever one team discovers a new strategy, the other one has to adapt. Kind of like an arms race situation, and it also resembles generative adversarial networks a little. And the results are magnificent, amusing, weird. You'll see in a moment. These agents learn from previous experiences, and to the surprise of no one, for the first few million rounds, we start out with pandemonium. Everyone just running around aimlessly. Without proper strategy and semi-random movements, the seekers are favored and hence win the majority of the games. Nothing to see here. Then, over time, the hiders learn to lock out the seekers by blocking the doors off with these boxes and started winning consistently. I think the coolest part about this is that the map was deliberately designed by the OpenAI scientists in a way that the hiders can only succeed through collaboration. They cannot win alone, and hence they are forced to learn to work together, which they did quite well. But then something happened. Did you notice this pointy, doorstop-shaped object? Are you thinking what I'm thinking? Well, probably. And not only that, but about 10 million rounds later, the AI also discovered that it can be pushed near a wall and be used as a ramp, and ta-da, got him. The seeker started winning more again. So the ball is now back on the court of the hiders. Can you defend this? If so, how? Well, these resourceful little critters learned that since there is a little time at the start of the game when the seekers are frozen, apparently during this time they cannot see them, so why not just sneak out, steal the ramp, and lock it away from them? Absolutely incredible. Look at those happy eyes as they are carrying that ramp. And you think it all ends here? No, 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 not even close. It gets weirder, much weirder. When playing a different map, the seeker has noticed that it can use a ramp to climb on the top of a box, and this happens. Do you think couch surfing is cool? Give me a break. This is box surfing. And the scientists were quite surprised by this move, as this was one of the first cases where the seeker AI seems to have broken the game. What happens here is that the physics system is coded in a way that they are able to move around by exerting force on themselves, but there is no additional check whether they are on the floor or not, because who in their right mind would think about that? As a result, something that shouldn't ever happen does happen here. And we are still not done yet. This paper just keeps on giving. A few 100 million rounds later, the hiders learned to separate all the ramps from the boxes. Dear fellow scholars, this is proper box surfing defense. Then lock down the remaining tools and build a shelter. Note how well rehearsed and executed this strategy is. There is not a second of time left until the seekers take off. I also love this cheeky move where they set up the shelter right next to the seekers, and I almost feel like they are saying, yeah, see this here? There's not a single thing you can do about it. In a few isolated cases, other interesting behaviors also emerged. For instance, the hiders learned to exploit the physics system and just chuck the ramp away. After that, the seekers go, what? What just happened? But don't despair, And at this point, I would also recommend that you hold on to your papers because there was also a crazy case where a seeker also learned to abuse a similar physics issue and launch itself exactly onto the top of the hiders. Man, what a paper. This system can be extended and modded for many other tasks too, so expect to see more of these fun experiments in the future. We get to do this for a living, and we are even being paid for this. I can't believe it. In this series, my mission is to showcase beautiful works.
By the way, you can probably recognize those graphs now. Like, there's a kind of like, yeah. So what do you can just imagine what they are. It's just reward, right? Did y'all think that was interesting? I think that's fascinating. Like, I would love to like be on a paper about this kind of stuff and like see it, like be a part of like seeing it for the first time. Okay, well, I guess that'll be it for today. I will, I guess like I'll finish this notebook and put it on my GitHub and also put it on Canvas. I'll post this YouTube video and the one from last week. And then next week, I'll be available all week for any questions about the final project, like your repository, anything you need, just email me and we'll set up meetings and get everything settled away. All right, so that would be it.